All right, so quick review from yesterday, right? We said if we want to find, what we're trying to do here is we're trying to find absolute extrema on an interval, right? On this interval. And you told me yesterday that absolute extrema can occur at endpoints or at relative extrema, peaks and valleys, right? And so the way we find those, of course, is then we're just going to find the derivative, right? Take the derivative, and we're going to find the zeros of the derivative. Those would be critical numbers, and then we'll find all the places where the derivative is undefined on our interval, and those are also critical numbers. And then we'll just check them with our table, right? We just look at our table and we compare. We found critical numbers at 0 and 1 here. We had endpoints at -1 and 3, and we'll just compare the values of the function there to see what's the biggest and what's the smallest, right? Okay, so let's look at an example that involves a trig function. Something like, how about something like this? Okay. What do we do first? Differentiate. Okay. So we end up with f prime equals, what are we going to get from the first term? Minus derivative of cosine tan. Okay, so we'll make that plus sine tan times the derivative of tan is 2. Okay. Okay, and then we want to find every place where our derivative is equal to 0 or undefined. Is it undefined anywhere? And why? No denominators, okay? And with trig functions, we got to kind of think about the behavior of our 6 trig functions. Let's have everybody close these up all the way here. So you can really, why don't you go close that up? So we can really think about this together. So we have our 6 trig functions, right? Sine, cosine, tangent and cotangent go together, secant and cosecant go together. Think about the composite trig functions, everything except sine and cosine. They all have a trig function on the bottom, right? Tangent, for example, is sine over cosine, right? Secant is 1 over cosine. And so does it make sense that all of those they're all going to have vertical asymptotes? Because they're going to be places where there are zeros in the denominator, right? And if you think back to trig, they all do, don't they? They're all periodic with vertical asymptotes. Okay, but sine and cosine are fine. If you think about what the graph of a sine function or a cosine function looks like, you remember this stuff. This is, what's a sine graph look like? What's sine of x? Yeah, it's just, right, forever and ever. Cosine is just phase shifted a little bit, but it's the same graph, right? If I take something like sine of, or cosine of 2x, I mean, what's that doing? It's just changing the wavelength of the sine wave, right? It's just accelerating it by 2. So all it's going to do, it's not really going to impact much. It's just going to make this thing a little bit squashed. But the point is, there are no vertical asymptotes, right? It's fine everywhere, isn't it? The domain is all real numbers, okay? Everybody see what I'm getting at there? So we can look at this right away and say, sines and cosines, no problem with, if that's our derivative function, and all we have are sines and cosines, none of them on the bottom, we're fine, right? We're going to get none of those critical numbers where the derivative is undefined. It's defined everywhere, okay? Does that make sense? Give me a thumbs up, thumbs down, thumbs sideways on that one. How are we doing? Okay, good, good. All right, so what about the other type, though? If we want to find the zeros of the derivative. So we got to set this function equal to 0 and solve. So that's going to give me 2 cosine x plus 2 sine 2x equals 0. What can I do here to solve this equation? Good, so for one thing, let's divide both sides by 2. We could factor out a 2, but because we're just solving an equation anyway, we'll just divide that 2 away, right? Okay, now there's something doesn't look good about this. Yeah, now think about this. Now this goes back to trig, but when we solve a trig equation, think about the steps involved in that, right? First of all, we have to factor it, hopefully, in terms of trig functions, but I can't be comparing apples and oranges here, right? I have to have trig functions of the same angle. So what's my double angle formula for sine? Sine 2x changes to what? How can I write that in terms of sine x and or cosine x? Remember? Not ringing a bell?
Over 2.
I just can't remember it.
Yeah.
I remember it.
Remember, okay. And probably at some point, before we get into too much tricks, we'll just, I'll just give you a sheet that maybe we just have some things to remember. Just because it's easier to remember than have to look it up all the time. Sine 2x is just 2 sine x cosine x. So we end up with cosine x plus 2 sine x cosine x equals 0. So what am I going to do now? Now I've got all the same angles in all my trig functions. Yeah, good. We're going to factor out a cosine x. Very good. We'll look for common factors. Our goal is to put this in factored form so we can just apply the zero product property. So we'll factor out a cosine, leaving us with what? Good, and so then now we'll just apply the zero product property and we'll find the zeros of the factors. So when is cosine x equal to 0? On our domain, look at our domain, from 0 to 2 pi. So we just probably need a unit circle to stare at here. Where is cosine equal to 0? And which one is cosine? Is that the x or y coordinate? X coordinate. So pi over 2 and 3/2 pi. Okay, good. So this is going to give us x equals pi over 2 or 3 pi over 2. Okay, how about this one? Let's look at this guy. So if I set that equal to 0, first thing I want to do is isolate sine x, right? So what's that going to give us then? If I set that equal to 0 and isolate sine x, what am I going to get? Negative 1/2. So where is that going to be the case? So that's the y coordinate, right? Where is the y coordinate equal to negative 1/2? Say it again.
Pi over 6.
Okay, so in quadrant 1, that's a good strategy. In quadrant 1 up here, we know if we use our little finger thing, right? We know that the point with coordinates, with a y coordinate of 1/2 in quadrant 1 has an x coordinate of what? It's pi over 6. It's going to be square root of 3 over 2, right? Does that make sense? Remember how you do that with your, so that would be that's going to be this one, isn't it? Because the x coordinate is going to be square root of 3 over 2, and the y coordinate is going to be square root of 1 over 2, right? And that's going to be the angle pi over 6, right? So if that's pi over 6, then so is that right there, and so is that right there, right? So what's that whole angle?
That's pi over 6.
It's good, 7/6 pi. We're going to go pi plus 1/6 pi, right? So one solution will be that, right? Pi plus pi over 6. And then what's this one going to be? Yeah, it's going to be the whole 2 pi minus 1/6 pi. So 11/6 pi. So those are our 4 critical numbers then, right? And all we have to do is just make our table. Okay, so let's go back up here, and I'm just going to copy all this stuff. Actually, don't really need that one, do I? I'll just copy this. All right, so if we make our table, endpoints are at 0 to pi. And what do we get in order here? Our zeros are going to be, what? Pi halves, 7/6 pi, 3 halves pi, 11/6 pi. If I write them in order, okay? Okay, like that. And then we just have to evaluate our function in those places. So what is f of 0? 2 sine 0 is 0 minus cosine of 0. What's cosine of 0? 1. So minus 1. Okay. Make sense? So there's one y value. How about pi halves? What's the sine of pi halves? So f of, let's do this down here, is 1, isn't it, right? Right? Times 2 is going to give us 2 minus, now what's the cosine of 2 times pi halves? 2 times pi halves is pi, right? So cosine of pi is negative 1, isn't it? So we're going to subtract negative 1. So I get 3. Good. About 7/6 pi. So sine of 7/6 pi. That's going to be down there, so, well, negative 1/2, good. So we're going to get our negative 1/2 minus cosine of
Did you already
2.
multiply by 2?
Oh, times 2, you're right. Negative 1, good. Minus cosine of 2 times 7/6 pi. Well, that's just 7/3 pi, right? Make sense? So let's think about unit circle then. Where is that going to be? 7/3 pi. That's, what's 6/3 pi?
2 pi.
2 pi.
It's just
So we'll go all the way around, plus pi over thirds is right there. What's the cosine of that? 1/2, good. So minus 1/2 is negative 3 halves. No, we did that, it's inside times 2, right? So we're negative 1 minus 1/2 is negative 3 halves. Okay, what about 3 halves pi? So f of 3 halves pi, 2 times, well, what's the sine of 3 halves pi? Sine? Negative 1 times 2. So that's going to give us negative 2 minus cosine of 2 times 3 halves pi. Well, that's the cosine of 3 pi, right? That just, there? So negative 1. So plus 1 equals negative 1. Can we agree? Okay, and then finally 11/6 pi. Sine of 11/6 pi is what? 1, negative 1/2, right? Times 2 would be, oops, 11. So negative 1, right? Did I do that right?
Yes.
Yeah, okay. Minus cosine of 2 times that, that's cosine of 11/3 pi. How many, what's that? What's 11/3 as a mixed number? 3 and 2/3. So we're going to go 1, 2, 3 pi, and then another 2/3 pi puts us down there, doesn't it?
Negative 1/2.
right? So the cosine of that's gonna be, cosine would be the cosine of this one, not right down.
All students take classes.
What is that? So what are the coordinates gonna be at that point right there? They're gonna be over in the x direction? No. Okay, think of it this way. Think of it this way. If we're 11/3, was that what we are, 11/3 pi? So we're 3 2/3, right? Well, that's just the same thing as 4 pi minus 1/3 pi, right? Well, think quadrant 1. If this is 1/3 pi, then that's got to be the small x coordinate and the big y coordinate, right? So this will be just 1/2, right? The x coordinates can be the same for both of those, right? So the x coordinate is going to be 1/2, but we're subtracting that, so we get -1 minus 1/2 is -3/2. Agree? Okay. Okay, so then what's our winner and what's our loser?
Yeah, but 2 pi.
Oh, 2 pi, whoops, got that. So sine of 2 pi is 0. Cosine of 4 pi is, at least I just go around twice, is 1, yeah, so -1. Okay, now what's our winner and what's our loser? So 3 is definitely the winner, isn't it? So that's our absolute maximum. And we have a tie. Good, so they're both, we have 2 absolute minima. The absolute minima occur at there and there, right? Okay, so okay, make sense? Okay, so let's take it real quick. Let's pull up the assignment. See if there's anything that doesn't make sense. I'm just gonna let you work on it. All right, so let's see here. Just want to see something here. So there's, I think I had one more bill. Oh, you know what? Actually, I forgot the intermediate value thing. Okay, so last issue then. Okay, extreme value theorem. This is really simple, but I just want to, one more thing. And then we'll look at a sample problem for this. You guys can tell me the answer to this. This is an existence theorem, right? So think of this as a picture theorem. Very simple stuff. So, what am I going to say? The title of this is the extreme value theorem. If f is continuous on the closed interval from a to b, then what's f going to have? Think about our whiteboard example of what it means to be continuous from a to b. can't have any breaks, so when I write it, what about my pen?
You can't.
You don't
pick
pick
it
I
up.
can't pick it off the board. So if I can't pick my pen off the board, think about what this graph is gonna have to do. Yeah, if I'm going from A to B, what has to be true? Yeah, there's gonna be a maximum, at least one maximum and at least one minimum, right? It could be shared, but we know we're gonna have a maximum value and a minimum value. Right? That's it. Okay. So let me pull up the assignments then. That's called the extreme value theorem. No big deal.
So how would you represent the maximum minimum on a horizontal line?
Well, okay, so what if it were a horizontal line? Then every point would be a maximum and a minimum. And that's kind of a weird example, but that would be the case. Okay, so here's the assignment then. Do these make sense here? Let's take a quick look at these. So assuming that we allow endpoints to be relative extrema, here's our function. Where are their relative extrema on this function? Everybody pause, just take a look up here, please. This is going to be just like one you're going to do. So what do you think? Yes, sir.
-6 and 6.
-6 and 6. Everybody agree? What about at 0? What's wrong with that?
It equals 0.
It equals 0. Yeah, and look what's going on here, right? Think what a relative extrema means. It's peak or valley, right? But mathematically, it's a place where the ant, if the ant takes a step away from that point, he's either going to have to go up or have to go down, right? Well, this is a little weird, right? But if we're going to allow endpoints, and that's, by the way, you run into things in calculus that are debatable. We could have a rigorous discussion in here, mathematical discussion, and with mathematicians, and there would be some mathematicians that would say, nope, endpoints can't be relative extrema, and some would say that they could. And so you have to qualify that every time and say, are we going to allow it or not? If we do, then that is a relative minimum, right? Because the ant cannot walk to the left, he can only walk to the right, and if he walks to the right, he's walking up. So that's the lowest point, relatively speaking, locally speaking, right? Same thing over here. This is the highest point locally. What about here, though? You might say, what's wrong with saying that the point next to 0 on the left is a relative maximum? There is no such point, is there, right? If you think it's the point next to 0 on the left, well, you actually are off by an infinite number because there's an infinite number of points in between the point you select and 0. It's this whole thing where I'm walking to the door, cutting my distance in half with every step. Hey, morning.
Excuse us.
Yeah. If I'm doing that, right, everybody agree I never get to the door, but there is no point that I ever stop. I can take an infinite number of steps, right? So that can't be a maximum and that can't be a minimum. Let's just see here. Okay, so that'll make sense, no problem.
Wait, so almost 6 and -6?
So this one would have been a local maximum occurs at 6 and a local minimum occurs at -6. Okay? Okay, these are no big deal, no big deal. No big deal. Okay. Okay, we're good, we're good. All this stuff you can handle, no problem. Okay, so on these, you have to use your textbook. I haven't changed these over to where I put the problems in yet. So you have to look at your textbook at Larson 3.1, number 8. Okay, it's just asking you to find critical numbers. Yeah, it's no big deal. No big deal. I just did a work day today. My guys still have so much to do on that.
I'm looking, every time I start 3-2, I have like 44 people, and you got, all 12 of mine started 3-2, I think now.
Yeah, yeah. So I got a ton of people that still need to finish stuff up. Yeah, so that one you got to look at Larson, but it's fine. You'll be fine.
On this,
Mm-hmm.
this is A.
Mm-hmm. So for a horizontal distance of 1, 2, 3, 4, 5, vertical distance is 1, 2,
I think it's 10.
is 10. Okay. So then what would it normally be? For 5 it would be 25. So, right. So then the dilation factor is going to be negative 10 over positive 25 is negative 2/5.
Can we get negative 10?
Because that's what the final, that's what our, see what I'm saying? So in other words, you could say A negative 10 times A, or sorry, 25 times A equals negative 10.
So a horizontal distance of 5.
Mm-hmm. The parent function value is 25. So 25 times the vertical dilation factor is negative 10, because that's what we get. The dilated distance is negative 10. The undilated distance is 25, right? So 25A equals negative 10, so therefore A is negative 2/5. Negative because it flipped, 2/5 because it compressed it quite a bit.
Yeah. Yes.
See what I'm saying?
Yeah, and times where I get it, so horizontal distance of 5 should be 25.
Right. That's the starting shape, and so you got to dilate it to get the curve that you took a picture of.
To get that point to that point's at 11.
But you don't care about, see, once you find H and K, then it's just like you're going to say, okay, from that vertex, what would the parent shape be? What is the dilated shape?
Yeah, and that point that's on there, that's the next point.
Well, it's just, it's a convenient point. It doesn't have to be the next point, it's just a point.
Yeah.
Right? So if the horizontal distance is 5 from the vertex, then the
That would
the
be
parent
saying
vertical-
X is 5.
yeah, right.
Yeah, and if you're just looking at the parent, and when X
Exactly,
is 5,
yeah, and
Y
we're
is
just looking at the
25.
shape, and the
I
shape
get-
of
I
the
get
parent
that.
graph is built from the horizontal distance squared is the vertical distance, right?
Yeah.
So then the parent graph would have gone over 5 and up 25.
Yeah.
So that's where you're
I
starting.
get. I get that.
And then you got to do this to it. Did I show you this? This is kind of cool. If I go to, oops, I
Decimals.
stopped